Hi, this is Dr. Fred DePiro, and this video is on modeling circuits via Thevenin and Norton equivalents, Part 1. Learning objectives here are to form these equivalents for circuits that contain resistors and independent sources. Prereqs are a bit extensive now. This is a culminating topic for DC circuit analysis. So mesh and nodal analysis will be very useful. Superposition is going to be needed, and also all our techniques that we use with what we refer to as equivalent circuit analysis, such as finding the resistance seen by a source and voltage and current dividers. All of those ad hoc techniques are all going to be useful here. So, why are these models, the Thevenin and Norton models, needed? Well, the models will replace more complex circuitry that is associated with a situation having two interconnected systems. So imagine this portion of the circuit here to the left of the dashed line. Imagine that represents some complicated system that we're going to model. Okay? For example, the state's entire power grid. So this is all of PG&E here. Their generation facilities, their distribution, everything. Okay? That's a complicated thing that we want to create a simple model of. Over on the right is another connected system, an interconnected system on the, say, downstream side, connected to that more complicated system. In this case, maybe it's just single resistor, a simple load like that, or maybe it's your house. So PG&E here, your house there. In between the two are what we refer to as a port, and it is a two-wire port connection. Right where this dashed line is, we put these little circles in there to symbolize the port connection. Now, often it's not necessary or maybe not even possible to know all of the internal details of a system that we need to connect to. So, for example, if I want to get my home, on the power grid, I don't need to know everything about PG&E and their distribution system. Okay? That's way more complicated than I need to know. This is an example of how having a simple model like a Thevenin or Norton model would be very helpful, because we don't need to know all those details in order to accomplish some task on the downstream end. Okay. And the Thevenin and Norton models provide a sufficient description for our interfacing needs. Okay, so what's the form of these models here? Well, each model includes port connections similar to the original. So we have the original up here. Here's the Thevenin and Norton. Original, Norton, Thevenin. Thevenin includes a voltage source and a series resistor. Norton includes a current source with a parallel resistor. They are dual forms. Now, these models are equivalent, yes. They sure don't look the same. The original, the Norton, the Thevenin, no, they don't look the same. So what is the nature of the equivalence? Well, the equivalence is from the perspective of the load, or this downstream subsystem, as it looks back into the more complex system that it's being driven by, or that it's connected to. That's the nature of the equivalence. A little more specifically. So if we covered up this section under the blue box and we have this load over here, the conditions for the load are identical, irrespective of whether it is actually driven by the original circuit, by the Thevenin equivalent to the original circuit, or by a Norton equivalent to the original circuit. That's the nature of the equivalence. And an even more specific example, suppose this load here was just a 50 ohm resistor. Well, if we take that resistor and connect it to any of these, the original, the Thevenin, or the Norton, then the voltage and current associated with that resistor would be identical, irrespective of which version that load is connected to. This is the nature of the equivalence. The load can't tell the difference. Conditions are the same. Okay? And that's from the load looking back, connected at the port, looking back into the system. Okay, so summarizing so far, what are these models and why are they needed? Thevenin and Norton equivalents provide a simple model of more complex circuits as seen from a port connection. The conditions for a load, for example, just a simple resistor, and those by conditions we mean the voltage and current for that load, are indistinguishable if the load is connected to either the original circuit, the Thevenin equivalent, or the Norton equivalent. Okay, so how do we find these equivalent models? Here's the Thevenin, here's the Norton. Well, for the Thevenin, we can see we need two parameters. These are model parameters, the Thevenin voltage and the Thevenin resistor. We need those values for those specific components. Similarly, for the Norton model, we need the intensity of the current source as well as the value of this resistor, the Norton resistor, Rn. Now, we don't actually solve for those model parameters directly. Okay? We don't solve for those. Instead, we solve for some intermediate parameters. So here's an introduction to the intermediate parameters that we solve for via a circuit analysis. Here you see some original circuit, and you see three intermediate parameters that'll be defined here. The first one, referred to as VOC, the open circuit voltage. That is the voltage between the two nodes at the port for the original circuit. It's the voltage between those nodes with nothing connected. Okay? So that load resistor, that downstream system, has been disconnected. And then we say, okay, what's the voltage between those two nodes? That's the open circuit voltage. Next, short circuit current. Imagine if we took a wire, connected it in between those two port connections, and then determined the current. That is ISC, the short circuit current. Now, take care in practice. This is not safe and can't be done in many cases. If you have a smaller device, lower power, yes, you could do this and make the current measurement. Obviously, you would not do this if you were trying to model all of PG&E. Okay, lastly, REQ, the equivalent resistance seen looking into the port. A couple quick comments here. First of all, this is with the sources off. So we deactivate the sources, the internal sources that are in this original circuit. And then the resistance that we're looking for is the resistance going from this top connection, going through all the various different paths, through series and parallel elements to get to this bottom connection here. It's the resistance looking in to that circuit. Okay, now we need to talk about the relationship between the intermediate parameters that are now defined and the model parameters. Fortunately, that relationship is easy. Okay, so we'll just take these one at a time here. Let's consider how each intermediate parameter relates to the various model parameters. Okay, here's the original circuit, the Thevenin model, and the Norton model. Okay, VOC, the open circuit voltage. So let's suppose we're given this original circuit, and we go through and we do the analysis and we find out what VOC is. Now, how does that relate to the model parameters? For example, how does VOC, shown here, relate to the Thevenin voltage? How much current is flowing through this Thevenin resistor with an open circuit load here? So no load resistor, it's open circuited. That load resistor is disconnected. How much current's flowing through here? 0. What's the difference in the node voltages on either side of the Thevenin resistor? 0. There's no current flow. They have to be the same. So therefore, V Thevenin is equal to what? V Thevenin is equal to VOC. They're identical because there's no voltage change here. Okay. Now, how does VOC relate to the Norton model? Well, that one's easier. Okay. The voltage between the port connection here is the same as the voltage across this Norton resistor, and we can get that just by Ohm's law, IN times RN. Recapping so far, for the open circuit voltage, if we found that in the original circuit by doing an analysis of it, we could use that information then, for example, to get the Thevenin voltage. They're exactly the same. Or to get some information about the Norton model. Next, how does the short circuit current relate to the Thevenin model? So here's that wire, that shorting wire in between the port connections, as you see up here. And imagine we did the analysis up here. We got the I short circuit, so we have that value. Now, how does that relate to the Thevenin model? Well, by Ohm's law, the short circuit current that we're seeing is V Thevenin divided by R Thevenin. Okay. Now, how does that relate to the Norton model? Well, let's see here. We have that shorting wire right here. So how would that short circuit current relate to the model? Well, the short circuit current is exactly equal to the Norton current because of the short itself. You can think of this as a current divider with 100% of the current going through the short. 0% of the current is going to go through the Norton resistor. Okay, recapping so far, the relationship between intermediate parameters and model parameters. Easy, no problem. For V open circuit, we have these relationships. For I short circuit, we have these relationships. One more to go. R equivalent, sometimes a favorite. Okay, R equivalent, to find it, again, we deactivate the sources in the original circuit, and then we find the total resistance, equivalent resistance from this upper connection down to the lower connection, often doing some kind of series parallel combos on whatever resistors remain in here after the sources have been turned off. So let's say we did that, and now we have this value, REQ. Now, how does that relate to the Thevenin model? And notice the sources are off for the Thevenin model and the Norton model when we're talking about R equivalent. If we're going to deactivate the Thevenin voltage, then we replace it with a wire. Therefore, R Thevenin is simply R equivalent. And now for the Norton model. If we're going to deactivate this current source for the Norton model, we replace it with a broken wire or an open. Therefore, Rn is simply equal to R equivalent. Okay, so here is a recap of the relationships between these intermediate parameters that we can find by doing a circuit analysis of our original circuit with the focus on the port. See, the open circuit voltage at the port, the current flowing between the port connections with a shorting wire, or the resistance looking into the port with the sources off. All of those quantities can be found from an original circuit by doing an analysis by any method you choose, node voltage, mesh analysis, equivalent circuits, whatever you want. Do whatever you need to do in order to get these parameters, and that will then allow you to find the model parameters. Now, a little bit of good news. Because of the interrelationships that you see here between these different parameters, when you go to analyze an original circuit, you actually only need to find 2 out of 3 of these quantities. Okay, 2 out of 3 of these quantities. That's because of all the different interrelationships. Okay, so here's a summary page. you see the original circuit and the port with each of the three intermediate parameters. You see the two models, the Thevenin model and the Norton model, and you see these relationships in between the intermediate parameters and the model parameters that we need. Once again, we only need to find 2 out of 3 of the intermediates. Okay, so this video was all about Thevenin and Norton equivalent models, and the cases that we looked at were situations that involved resistors and independent sources.